Electric flux is the total flow of an invisible electric field piercing a specific area. It is a way of measuring how much of that invisible force is actually passing through a boundary in space. To calculate that flow across a surface, you typically have to use a surface integral. It is a massive computational headache. You have to account for tiny variations in the field's angle, adjust for changing distances, and continuously sum up an infinite number of infinitesimally small patches of area. Look at this diagram. Placing a charge inside a perfect sphere collapses the math. With every surface point equidistant, the field is identical everywhere. The calculus cancels, leaving Gauss's law. Total flux equals enclosed charge divided by free space permittivity. We can deform the sphere into a cube, a pyramid, or an uneven blob. As long as the boundary is completely closed, the same number of field lines have to pass through it. The size and shape of the container do not change the total flux. In this situation, we see multiple charges scattered inside and outside a surface. While the total electric field is influenced by every charge present, the flux formula only cares about the charges physically trapped inside the boundary. The charges outside are mathematically irrelevant. Gauss's law takes a grueling surface calculus problem and replaces it with a simple accounting question. What exactly is in the box? This diagram outlines a classic physics trap. We have a charge hovering exactly half an edge length above a flat square. To find the flux through just that square, you might be tempted to set up another integral. Instead, we can build imaginary walls. By conjuring 5 more identical squares, we construct a complete box, trapping the charge perfectly in the dead center. Since our original square is one of 6 identical faces sharing the total flux, we just divide the Gauss formula by 6. Look at this scenario, where the charge is resting directly on the outer edge of a closed cube. The symmetry is broken because the charge is only partially enclosed. To restore the symmetry, we stack 3 adjacent imaginary cubes against the first one. Now we have a larger 4-cube block with the charge buried in the absolute center. Because our real cube is 1/4 of this symmetrical system, the flux passing through it is exactly 1/4 of the total. We can apply the same logic to a charge resting squarely on a single corner of a cube. By slamming 7 additional imaginary cubes into place, building out, back, and up, we encapsulate that corner charge in the center of an 8-cube megablock. The flux through our original single cube is exactly 1/8 of the total. Notice that the 3 faces touching the charge are parallel to the field lines, so they catch 0 flux. All of that 1/8 flux must exit through the 3 faces that don't touch the corner. Divide by those 3, and the flux for a single opposite plane is exactly 1/24. This is how we use space like a Lego set. If a problem lacks symmetry, we just build imaginary geometry until the charge is perfectly centered. The logic of centering a charge within a box scales up to long strings and massive volumes. The objective is simply determining exactly how much charge is caught inside the boundary. This schematic shows a hollow cylinder harboring an internal charge. We know the flux through the curved barrel, labeled B, but we need to isolate the flux exiting just one of the flat circular end caps, surface A. We start with the total Gauss flux and subtract the flux of the curved barrel. The leftover amount must be split evenly between the 2 identical end caps. Divide that remainder in half and we have isolated the flux for a single flat plane. Here we have a charged string threading through an imaginary cube. To find the maximum possible flux, we have to find the orientation that captures the most charge. Since flux depends on the enclosed charge, we maximize the length of the string trapped inside. The longest internal path in any cube is the diagonal stretching between opposite corners. That body diagonal is the side length times the square root of 3. This drawing takes an infinite line of charge and slices it off-center through a spherical boundary. By drawing a right triangle inside the sphere using the radius and the offset distance, we can use the Pythagorean theorem to calculate the exact length of the trapped chord. Multiply that length by the linear charge density and we have our enclosed charge. Whether we are stacking virtual boxes or drawing chords across spheres, Gauss's law turns advanced calculus into basic geometry. We started with an intimidating surface integral and bypassed it entirely by manipulating cubes, cylinders, and spheres. These Gaussian surfaces are entirely conceptual tools. There are no invisible boxes in nature. We project these shapes onto reality to force mathematical order onto a complex electric field. This method is effective because the electric field is tied to the geometry of its source. When we align our boundaries with that inherent structure, the complexity of the math vanishes, and the spatial logic of the field snaps into place. Gauss's law shows us that when faced with an impossibly complex physical reality, the solution isn't necessarily harder math. It's shifting your perspective until you spot the symmetry.